welcome back. So that was a lot to think about, but there's a lot of good material here for us to consider. So baseline power plants are exactly what their name implies. They provide the baseline power that's pretty steady throughout the year and throughout each and every day. Peaking power plants are brought on as they're needed. So if you have a big summer heat, like we're having in Michigan right now, a lot of air conditioning units will be brought online. Those are huge power hogs, and so we'll have to add peaking power in order to meet the needs. Coal and nuclear fuels are generally the fuels that are used for the baseline power plants, and natural gas is preferred for peaking plants. And that's associated with the hardware. Some of those big power plants can take over 24 hours to start or to cool for maintenance and things like that. Whereas the natural gas can come online in hours. So those can spin up very quickly. But you can also imagine, just think about the mechanics of that. You're spinning a turbine up to speed in hours. That's huge thermal expansion, material fatigues, all these challenges associated with making something that big spin that fast at those temperatures. So lots of fun problems and challenges associated with moving things quickly, providing power quickly. And now let's throw a whole new set of gears into the problem when we talk about sustainable power generation. Because things like wind farms provide intermittent power, right? We can't just dial up the wind when we need it. We can add more coal or we can add more natural gas. We can't add more wind and we can't add more solar. So they provide a whole new challenge for regulating the grid. They're sort of, because of that, they're intermittent. They can't really be relied on for baseline power. They're not quite peaking power, right? Because I can't spin them up or just dial up wind farms when I need them. So I'd place them in the load following category, although they're kind of a category in and of themselves. Solar power towers, which we haven't discussed in detail, are essentially heat sources for Rankine power supplies. The catch is, of course, a solar power tower can only generate power when the sun's in the sky. There's all sorts of clever ideas and methods, though, that you can use to bank that power, store that power, that heat energy, so that you can have less of a diurnal shift in the power generation for those systems. So I would actually put a solar power tower in a baseline category. That's where they'd like to be, is to be able to generate a steady amount of power while using heat storage in order to, again, even out those diurnal fluxes. So hopefully that gives you a lot of things to think about, different issues associated with stationary power. Okay, so last time, we've been looking at that steam power cycle quite a bit. We've done a lot of analysis. We looked at our numbers. We came up with our 30-ish% efficiency. We said, wow, 64% of our energy in, so that'd be your coal, your nuclear reactor, your solar power, whatever it is, if it's being used in a steam cycle, is going to actually be rejected as heat. And I'll tell you, nuclear power plants have even lower efficiencies because they operate at lower temperatures and pressures. So they get down in the 20%, 30% range. How can we do better? And we can. I promised you that there were methods to dramatically improve the thermal efficiency. And the catch is here is I'm going to redefine the efficiency. So what I'm going to do is suggest that instead of making power plants that only generate power, that we instead do what's called cogeneration, or combined heat and power. So we take systems that are actually designed specifically to generate both heat and power as their output, and then we get to change the definition of thermal efficiency, and those systems can be very, very high efficiency. Okay, so that's what's shown in this figure here. On the left, we have the power plant example, where we have 75 kilowatt hours is just an arbitrary unit of input that we have here for my example. And our power plant is actually a pretty good power plant at 40% efficiency, and that generates about 30 kilowatt hours of electricity, but 45 kilowatt hours is rejected as heat. Take your typical boiler or furnace. They actually can be very efficient. 80% is actually very conservative. I can make a boiler or furnace that's a very high efficiency. So again, somewhat arbitrary units. This is just for my example here. I have 69 kilowatt hours coming in as energy in, or fuel, 14 kilowatt hours are wasted as heat rejected to the environment, or losses in this system in this case, which may be heat transfer losses. It could be other losses as well. And 55 kilowatt hours are generated as heat. So what if I said, I'm going to take this, my heat transfer that's rejected from a power plant, and instead use it to create a desirable output of heat transfer. So I'm going to combine purposes for my power plant. I'm going to have it generate power and heat simultaneously. So that's what this cogen plant, cogeneration or combined heat and power is what you also see them referred to as CHP power plants. And in a cogen power plant, let's take my energy here as 100 kilowatt hours in. If I have an 85% efficient plant, that generates 85 kilowatt hours of electricity and heat, and only 15 kilowatt hours is wasted in terms of losses in the system. The CHP plant can be much more efficient than the power plant independently. And what I've done, again, is a little bit sneaky, is remember I said for a cycle we're going to define the efficiency as being what you want divided by what you paid for to get it. Well, you want net power out of a power plant, but you also have some desirable amount of heat transfer out as well. And what you paid for to get it is the heat transfer in. And so this is my combustion of fossil fuels, my nuclear power plant, my solar power tower, whatever that heat source in is. Once I get to sneak in and add the heat transfer out as part of my metric for defining the efficiency of the cycle, these power plants have very high efficiencies. And if you think about it, you always generate waste heat when you make power. That means we always have a heat source that we can use for different applications. I'll give you an example. At the University of Michigan, we have a cogeneration power plant on our campus. And that power plant provides power and it provides heat that's used to sterilize equipment at the hospital, at the University of Michigan Hospital. So there we have a need for both high pressure steam for heating and sterilization purposes. So if we can do that in general, that's going to lead to a much higher thermal efficiency for our power plants and our boiler/furnaces type applications. So that's a very desirable goal. Having said that, so now I've said, oh, hey, look, we're always going to generate waste heat whenever we have a power plant. I want you to think about what are the challenges of building a cogeneration power plant? What are some of the important issues you need to consider? And we're going to do a little mini example. We won't go through the numbers specifically, but we'll go through the thought process of how you would identify the numbers for a specific application. In principle, this is a great idea. In practice, it's a lot harder than you might think. And for a system like, let's say we have a power plant that's powering our hospital and it's providing the sterilization resources, that's a particular facility which has to be able to meet the demand at all times. 24 hours a day, 7 days a week. So there's got to be some safety factor associated with the power generation and with the heat transfer that's provided by that power plant. So I'm giving you some ideas of what I want you to think about. And that's what we'll discuss next time.